guess I can share the screen. So this is the distribution, and looks like okay. As you can see, I think there's a problem for question number 5. So that's why I give full credit for everyone for that. So the total mark is 18. So let's get started about the, so you can see the distribution is okay. So let's get started about the question. So I think in the answer, the first answer I have is C, but it should be B, but I changed accordingly. So this should be reflected accordingly. So the question is saying the Hang Seng index is uniform between 10,000 and 30,000. Can you see my screen? Yes. So the mean will be just the 2 boundary divided by 2, right? Because it's from 10,000 and to 30,000, right? And the height will be just 1 over 20,000, and expected value will be just this area, right? Times the value, but basically just the average, right? It's the midpoint, right? So we just in the middle. So this is the answer should be B, but I think initially I write C, but the answer is correct. So it should not be an issue. I hope that's okay. Second question, I think it's uniform. The variance is right if X is uniform between A and B, okay? And then the variance of X would be B minus A squared divided by 12. So that means it's 35 minus 15 squared divided by 12, and then give you 33.33. Okay, so that is how we're going to do that part. Is that okay? That's all right. Let's clear the drawing and go to the next one. This one is GDP growth, right? And again, we are relying on, say, between 4% to 10%, right? The difference is 6. So the height is 1 over 6, right? It's higher than 8%. So it means that 8% here, this is a probability, right? And you can just calculate the area, which is 2 times 6, right? 1/6. So it's 1/3. So it's 33. Or you can directly use the probability function, which is if X is uniform between A and B, then will be X minus A over B minus A, right? And what we have is 1 minus f of x, right? So that's why it's 1 minus 8 over 4, 10 over 4, also give you 1/3. Is that okay for this one? Is it okay? Good. So for this one, is asking exponential with mean 10, right? So x has exponential with mean 10, which means that the parameter is 1 over 10, right? Because usually it's theta, right? Theta is 10 over 10, or put it this way, with theta or lambda, right? And 1 over expected x is 1 over lambda, right? That means 10 is equal to 1 over lambda, okay? That means lambda is 1 over 10, okay? And variance of x is 1 over lambda square. And those of you who actually asked me why is not 2, then probably he either forget the lecture or didn't miss the lecture and don't know. I mean, I think in the class we already explicitly says there's no 2 there, okay? It's a typo. And if you also check the proof, it's also 1 over lambda square. So those who ask me should try to read the video class again. That was 1 over lambda square. Okay, so that means the variance is 1 over 10 square. So it's 1 over 100. Sorry. Sorry, typo here. Is 1 over 10, so it's 100. Okay. Any question? Just make sure that you remember this. There was a typo in the handout, but I think we already stated in the class, so make sure that you remember there's a typo over there. Okay? Any question? So next, question 5. I guess I get the answer right, but I think there's some problem where I press the calculator. So for your purpose, this question I drop it because there's a typo in the last answer. But here the mu is 10, right? So that means the lambda is 1 over 10, right? So that's why we have the f of x, right, is 1 minus e to the lambda x, which is 1 minus e to the, maybe put it this way, what we want is f of 5, right? So that's why it's 1 over 5 over 10, which is 0.393. Sorry for the wrong answer, but don't worry. In the final exam, there will not be any multiple choice, so you can always there's no worry about the answer as long as you get it correct. Okay. Any question? If no, then we go to the next one. Question 6. And this one is asking what the value of cumulative diffusion is this. So it's probability z less than z is 0.8770. Okay. It's asking what's the value of z, give you this one. Okay. So there, in this question, right, the way we teach is we know you can use a norm, standard this, right, and try different value, right? You can try norm this and put 0.18 true, give you which value, right? You just try all 4 value, then you are done, right? So let me show you the, can you see the Excel? Can you see my Excel spreadsheet? So norm, standard this, and say, what's the choice there? Say 1.16, and then 4 is true. Okay, so give you 0.87698, right? So you have to try all three answers to get the right answer, right? So here I want to tell you there's another function that will directly give you the answer. It's called the normal inward. Hopefully you can see. So there will be norm, standard inward, and you want to find 0.877. Okay, then give you this answer. Can you see that? So what is the test? Okay, so that is the reverse of that. Is that okay? Anyone can hear that? Can I say yes? Good. So normal dot s dot inward, it will be the thing we needed to let me go back to the questions we have. Where's my question? Sorry, I need to find my question. Where's my question? Oh yeah. So the next one, what the question is asking is for what value of z the cumulative is 0.2, right? So the same question, right? We just need to invert, right? We use the same trick again. Let's do it. So is norm as invert, and what we want to invert is 0.2090. Is it the question? Let me check. Yes. So just that's why it's negative 0.81. Is that okay? Of course, you can try the three, but because multiple choice, you can try, right? But if you don't, then you need to figure that out. So question number 8 will be some more straightforward, right? The question is asking the probability that x is between 54 and 47, right? And x has normal distribution with mean 50 and standard deviation 2 square, right? So you can rewrite it as z, right? 54 over 50 over 2, okay? 47 over 50 over 2, okay? That gives you negative 3 over 2, z, and 2, okay? So it's easy to see this is f of 2 minus f of negative 1.5, okay? So let's see how we do the Excel. Where's my Excel? Okay. So we need f of 2. So norm, standard, this, okay? 2 minus norm, standard, this, negative 1.5. Okay. we need to say true. This is Excel. If in the Google spreadsheet, you don't need that. Okay, so it's 0.91. Okay, so it's 0.10. Okay, so that's why C, and it's 0.10. Okay, so the very last question is sorry, it should be kg here. What it said is the mean, right? The mean is normally distributed. So the X has normal distribution with mean 3.2, standard deviation is 0.8, right? And asking the probability that X is less than 2.2, okay? That means is Z is less than 2.2 minus 3.2 over 0.8, okay? And it's just 1.25, right? Negative 1.25. And let's check. Okay, this is norm dot s dot invert dot this. Okay, negative 1.25, true. So this is the answer. So that's why the last answer is 1.05. Okay, so its closest is A. Okay, any question? Any question about the quiz? If no, then let's briefly talk about review the sampling distribution before we have a break. So let's spend a little bit to review, and then we'll review, and then we only start the new material at the break. Okay. So let's get started. So just review a little bit what we have last class. So on Tuesday, we talk about sampling distribution. Can you see my screen? Okay. So very quickly, just to remember, simple random sample means every element will have equal probability being selected, and that will be selected independently. Now, this is sometimes easy, but when you actually data you got from the real world is this question, whether this requirement is satisfied is not clear. But anyway, for our derivation, there's no problem, okay? And of course, if you really going to get a data from the field, from the real world, you need to figure out more advanced technique, right, when you have to do it. But anyway, and the sample mean is the mean of the sample, okay? That means that each observation is a random variable, okay? Because before you actually get a sample, you don't know what it is, right? Because each sample, each observation in the simple random sample will follow the same distribution with the population, okay? And each sample, each observation is different. So the sample mean is also a random variable, okay? Because each observation is random variable, and sum of the random variable divided by number of sample size, then it's also a random variable, okay? Please be careful, X bar is a random variable. And something we will do after the break is to prove, to show you why this random variable have expectation equal to the population mean, okay? So it means that if you do sample mean over many samples, the average value of that will be equal to the sample mean. Okay, so that means that sample mean is a good way to estimate the population mean. Okay, so later you will see this unbiasedness. And as we said, let's a break of 15 minutes, and then we come back to talk about the rest of the chapter. So break until 1:30, and I'm here to answer the question you might have. So I guess break is over. Let me know if any question. Now we are going to continue. Can you see slide? Yep. So we are going to show you why this is true. Okay, we're going to show you why the expectation of sample means population mean. Okay. Well, quickly, let's consider the example, and then this will show you why this is true. So we have three numbers, okay, 1 and 2 and 3. And usually, if this population, the sample mean is 2, okay? And sorry, the population mean is 2, okay? Now consider the sample with sample size 2, okay? If sample size 1, then it's clear the mean is 2 because the sample, the sample you get is 1, 2, 3, each one equally likely, and 1/3 of 1 plus 1/3 of 2 plus 1/3 of 3 is equal to 1. So equal to 2. So if sample size of 3, again, the same, because the only one possibility is 1, 2, 3, and then again, the idea will be the same, okay? So let's try the sample size 2, and then actually you can see the same thing carry to size of 3. So simple random sample means the first one is x1, the second one is x2, and for x1, right, each of them will be equally likely. Will be 1/3 is 1, 1/3 is 2, and 1/3 is 3. Same for x2, okay? So if 1 and 1, that means 1. 1 and 2, that means 1.5. 1 and 3, the mean is 2, okay? So what is the mean of this, all the sample mean, right? Because each is 1/3, this is 1/3, right? You have 1 and 1 is 1/9, okay? Each outcome is 1/9, okay? So that's why 1/9 plus 3 of will be 2 of 1.5, right? 3 of 2, 2.5, and 1 of 3. So the average is 2. So you can see the mean of the sample mean, or should be more accurately, right? Should be the expected value. Okay, because the mean is not really a very good definition because we don't define, but mean is in our model is equivalent to the expected value. Okay. So I got a question. Someone asked me for the assignment one where to put the reference because this is the same as all the poster you do, right? You see the poster at the bottom or somewhere say the source. Okay, you look at newspaper. Every newspaper they do the same. So you do that, or you can make a longer reference. That's fine. Just follow the standard way. Okay. Okay, here we do the formal proof for that. So the formal proof for the sample mean, right, is the expected value of the sample mean, right? Sample mean means sum of the x over n, right? This 1 over n can be taken out, okay? Because expected a of x is a expected x, okay? So that's how you get here. And how you hear from here is because x plus y is x plus y, okay? Expected value of the sum is sum of the expectation, okay? And then for each one is mu, okay? And the n of them, that's n mu, and n cancel out, give you mu, okay? So that's why the mean of the sample mean is the population mean, okay? Any question? Any question? No? Okay. So the next part is we know the mean and we want to know the dispersion, right? So how the sample mean is, okay? Turn out the variance, okay, is much more funny. It's related to the sample size, okay? The larger the sample, the smaller the variance is, okay? And it should be someone asked me the question, can I put the reference at the other page? No, just put the same page, one page only. Everything is one page. Everything on the same page, okay? So that determines sample size. The reason why is the following. Suppose you have sample a lot of time, right? Then n become very large, okay? The sample mean should be, the variance should be close to 0, okay? The reason is like, if you do a lot of sample, the sample size is very big, then basically you are each time you're getting the whole population, right? So then the sample mean will be exactly population mean, then there's no variance, okay? Just to graphically means, right? Suppose this is the distribution, whatever you like, right? And each time you just picking every single thing, right? Because n is very large, so you do random sample, but you do a lot of time, then basically get everything there, right? And then that means that every time you get the sample mean is exactly to the population mean, that means there's no variation. Then it should be close to 0, okay? And the exact formula is over n, and then which we'll prove, okay? One technical term you need to notice is standard error, okay? Which is the standard deviation of sample mean should be, I missed the sample, but I hope it's clear. Which is take the square root of this, so it's sigma over root n, okay? So now I try to give you some example, justify why this formula makes sense. Is that clear what we are doing? Okay, what it means is each time you have, suppose you do one sample, right? You got one sample mean, okay? And you do another sample, okay? You got another sample mean, okay? And then you do another sample like C, you got another sample mean, okay? And the question here is, there are many sample mean there, right? What is the variance of this sample mean? Okay, so that is the idea. Okay, I hope that is clear. Any question about this? Okay, people keep asking me the assignment one. So assignment one, you just put the source of the data in the poster should be right, because this is standard way to do it. If you submit it, I suggest you submit again to make sure you conform to the requirement. Okay, I think that's standard way. Yeah, I don't think for this one, I don't think you need to, because it's graphic. So I don't think there are a lot of word to be there, right? If you want, you can do it, but I don't think for this one you need to. No, you don't need. Yeah, no need, no need. Oh, someone asked me whether you need to do the verify. Yeah, you don't have to verify. Yeah, you don't. I don't think we need to, right? Yeah. Well, the reference is just say the source, right? Just say one sentence source is where. I don't think you just standard way. Look at all the other standard poster. You just put the simple something like source, right? Maybe just like Hong Kong Statistic Bureau 2010, and that's it. And the more detailed reference you can put in Excel. Just cite the source. I don't think it would be require a lot of space. Just any further question? I don't see you need a lot of space for the reference. Unless your data you have compiled from tens of thousands of sources, I think you have only few sources, right? The detail of this source, where to get it, you can put in Excel, but you don't have to design this. Yeah, you don't. Yeah, you don't have design. Yeah. Okay. Any more question? I guess somewhat you need to learn how to be. Anyway, it's okay. So again, we have population with three numbers. Okay, 1, 2, and 3. The sample mean is population means 2 again, right? And we know the variance of this population will be right. 2 minus 1 square is 1, right? 2 minus 2 is 0, plus 1, right? Is 1 minus 1 square, right? 2 minus 2 square plus 3 minus 2 square divided by 3, because each one will be drawn 1/3, right? And so that's why 2 for 3, okay? And again, sample size 2, 9 possible cases, right? Each pop is equally likely, right? So why we have shown sample means 2, right? So how to calculate the variance, right? Is 1 minus 2 square times 1/9, right? And then you do the same, right? 1.5 minus 2 square over 1/9, and so on and so forth, right? And here you can see 1 and 3 are different from 2 by 1, so there are 2 of them, okay? And these 3 are 2 minus 2 will be 0, okay? And then there will be 4 of them, which is different from 2 by 0.5, so the 4 of them. And you calculate this, right? It's 2 times plus 1 over 9, okay? So it's 1/3. And 1/3 can be, we write it as 2/3 over 2, right? 2/3 is actually sigma, okay? Over 2, which is n, sigma square over n. Someone asked me why the 9 possible sample, because this is a simple random sample. So it's sampling with replacement. So once you draw, you put it back. If you draw, then why is, I'm asking why not 3C2? If 3C2, then basically we are drawing without replacement. So the first number you draw will be different from the second number you draw. So it's not equally likely. Is that Henry? Is that okay? So, but if you do that, also it's possible to do that. If you do that, then you calculate the sample with a different way. But I just do the sampling with replacement. I think the answer will be same for with replacement, but I didn't try. That would be easier for this one because this is just for illustration. Okay. And the main reason is because we want this every single element to be chosen with equal likelihood, right? It's because this is 1/3, this is 1/3, this is 1/3, and we have simple random sample, so that's why we do it this way. And if you do the way you mentioned, it's not simple random sample anymore, it would be something else. Why there should be 1 minus 2 squared? Because sample mean is 2. So the mean of sample mean is 2. Because you average them out. This is 1 times 1.9, 1.5 times 1.9, and add them up. It gives you 2. And the variance will be each observation minus 2 and square. Is that okay? Keaton is okay? Good. Any question for this one? This is just illustration why this is right. Of course, we prove it in general case now. Okay, I hope that is fine. So now we are going to prove the general case why the variance is 1 over n, sigma have 1 over n as a correction factor. So the variance of the sample mean, right, with the variance of this is a definition. And this is summing all the observation over n, right? And here to here is variance of ax is a square variance of x. Okay? And from this to this is because xi and xj are independent. Okay? And when they're independent, variance of the sum, okay, will be sum of the variance. Okay, so that's why you can put the variance inside because variance sum is sum of the variance because they're independent, okay? And each one is sigma and n of them, so that's why n sigma square. And the n and n square cancel out, so that's why sigma square over n, okay? So that's the idea. Is that clear at this point? So what we have shown, just to remind you, is expected X bar is mu, which is nice, unbiasedness, and the variance of X bar is sigma square over n. Okay, so that is the idea is the variation of sample mean is smaller than the overall population variance is much smaller. Okay. Is that okay? No question? So I hope now you're ready for example where 2 and 4 comes from. So someone asked me the question, let me go to the previous slide, where 4 comes from. So sample is 2, we have 9 of them, okay? And they're different from 2, there's 1 and 3, okay? Because 1 minus 2 square over 9 and 1 minus 9, 3 over minus 2 square. That's the 1, okay? And that's why you have 2 of them. And where the 4 comes from, because there are 4 of them, maybe use other color, 1.5, 1.5, 4 of them. So 1 over 9 will be 1.5 minus 2 square, 1 over 9, 1.5 minus 2 square, plus 1 over 9, 2.5 minus 2 square, 1 over 9, 2.5 minus 2 square. And the remaining, these 2 are 0. Okay, so that's why like this. Okay, so it's okay. I mean, feel free to ask me a question if you have any, but this is just illustration, right? Why this is true. The real proof is this one, but for purpose, I think you understand this concept and we're already done, right? Because this is exactly showing this formula here, okay? Now that gives us I think that is the single most important theorem in this class, and this is the thing that I hope you pay attention to, okay? Because this is the most important thing. So we already know the expected value X bar is mu, and variance of X bar is sigma square over n, okay? We know that. We just prove it. So the question is, what is this distribution? What is that, okay? And this is very important, because central limit theorem, okay? It means if the sample size n is large enough, okay? And then this sample mean will follow a normal distribution, okay? So this is mu and sigma, we prove it already, so it doesn't really need to prove anything. Besides, we want to prove it's normal. And this is beyond the scope of this class to prove it, okay? And for application purpose, what do you mean by large here? Large here is when we think about the sample is usually is more than 30, then this apply, usually we say, okay? Less than 30, then we have to be careful, okay? More than 30 or something, then it will be okay for application purpose. And what does that mean? It means that X bar minus the mu over the sigma over root n is standard normal, okay? So this will be proved to be very useful. Why? Later you will see the reason why we care about this, but this will be reserved for the next class to show you why this is important. But the interesting part is when n is big enough, we know how sample mean, even though the x has any variable distribution, okay? The funny part is X bar is always a bell curve with the mean mu, variance is sigma over n, okay? So that is the key. Is that clear? What does that mean? Okay, I hope that is absolutely clear because this is the most important thing in this, I would say in this course, this most important theorem. Hopefully you remember in your mind, just repeat the statement. If the sample size get larger and larger, the sample mean of the simple random sample will have a normal distribution, okay? With, of course, the mean has population mean, right? And the variance will be 1 over n of the original population variance, okay? That is the key thing, okay? So let's, if there's no question from you, I hope you would, let's apply it, okay? So the population mean is 5 and the variance 64, okay? Which sigma square is 64. So this implies sigma is 8, okay? And sample size 100, okay? That's large enough for the central limit theorem to apply, okay? So what is probability no more than 4? So which is less than or equal to 4, okay? And remember this, we'll have a normal distribution with mean 5, 64 over 100, okay? And that means we need, then we convert to Z, right? Which is, this is the mu, right? And this will be square root of 64 over 100, okay? Which is 8 over 10, right? Which is 0.8, right? Negative 1 over 0.8 is negative 1.5. From here, you do the Excel, right? Will be the norms, then this negative 0.125 and then true. Okay. So this is how you arrive at solution. Is that okay? And in the next topic, you will see why we will need that, okay? Why we need to calculate all this less than 4 or more than 4, okay? We'll be leading to show you the two things, estimation and hypothesis testing, but this will be reserved for the next 2 chapters. This calculation you repeat a lot of time. Later you will see. Okay, but so far is any question? Any question? Is it okay? Can I have you say yes if that's okay? Because that's just a very, very, very important. Someone said, look at the Excel, give you different answer. Let's try, because if that's the case, let's do in Excel. So is norm, oh yeah. It's oh, I missed the 0 there. Should be 105. Okay. So it should be, we have calculated already actually in your, so it should be 1, sorry for the typo, it should be, just to make sure that it should be 0.105. Okay, so there should be 0 there. Make sure you correct your slide in case you do revision in the future. Okay, sorry. Now, thanks Peter for reminding me. Thanks, Peter. Any question? Is that okay? So no more question? Good. So the next part will be give you the same thing, but now the data is either 0 or 1. Okay, a special case. Okay, this special case is very important in the sense that sometimes the data is either 0 or 1. What is sometimes data 0 1 is say say the data is like, do you have you say suppose the X is like, have you visit say Europe? Okay, have you been to Europe? Or have you tried this product? Or has accident take over, right? So, and this is sometimes even we often is binomial trial, right? Because every time observation 0 1, right? Or in general, it's a binomial trial, right? You just look at the observation, ask whether he had done this true or false, right? A lot of survey questions we do have done there. Or xi or x1 or 0 will be usually audit purpose, right? You try to see whether this one maybe the product is what you observe, the audit, follow the audit process or no, right? Yes or no question. Yes, no question, right? And then interesting part is when you have binomial trial, right? The variance and the mean are related, right? Because this is P, this is 1 minus P times 1 minus P, right? But we use pi here. And the population, right, average is pi here, usually called proportion, right? Because the summation, the mean, usually called the P, right? It's just sum of the xi over n, right? So it's between 0 and 1, okay? And the sample average or the sample proportion, right, will be just what we have just said, okay? Is there any question for this one? Just in a special case where 0, 1, the sample mean is called sample proportion. Okay, there's nothing new here, but except we know the sample mean is related to the variance. Why is it important? Let's see for the next slide, you will see why we are distinguishing this. Okay, and the sample variance, right, or the variance of the sample proportion, right, will be, you replace this pi 1 minus pi over n, right? This is the sample variance, right? Variance of sample proportion. And the standard error of the proportion will be the standard deviation of this sample proportion, right? The square root of that, okay? So why this is interesting? It is because when the sample later, when the central limit theorem applies, okay, we have pi, the variance also pi, okay. So the sample proportion is based on this, only depends on the pi by itself, okay, and compared to the case where this, okay. And in the next chapter, you see this, okay, is easy to know, okay, and this one is often very difficult to know, okay. But for this case, we just need to know this one, right? And this one will already give us this answer, okay. So that's why our life is much easier for proportion than usual sample mean, okay, because of the variance can be estimated if we estimate sample mean, okay. So that's why we separate the proportion as a special case, because this has some special feature. Is that clear? This is just a special case when we x are just 0 and 1. Is that okay? Any question? No? Is there a question? No, okay. So the next slide is trying to tell you that there's something we often use is called binomial approximation. Okay, is remember when you have binomial, right? It's somewhat like this, right? It's a lot of somewhat like bell shape, right? It's a binomial NP. Okay, what it said is binomial NP. Okay, can be approximated as normal NP times 1 minus NP over N square. Okay, so that's why you have here, we write NP is the pi, okay? And the N cancel out, okay? So when you have, usually this is why when you have binomial, you can approximate by normal, okay? Just the question is, if the question asks X is a binomial, X asks between 3 and 4, maybe 13 and 4, right? Suppose X has a binomial of 100, okay, over maybe half, okay? You want to calculate this, okay? You calculate this will be a very complicated task, okay? What it says is you can consider it as a normal, okay? When we say N pi and N times 1 minus pi is at least 5, which satisfies in this case, then you can convert it to Z, right? So that is the idea. Okay, so that means that the sample proportion, okay, is again when this at least 5, we will consider this is the N, okay. This is a central limit, or you can invoke central limit theorem, okay. One way or the other is fine. Okay, so let me show you the approximation. The proof is just some of this observation. If this is 0 or 1 data, right? That is a binomial distribution with, sorry, this should be, typo should be N pi, okay? And then when we say this binomial can be approximate at least 5, okay? Then that means, okay, the sample mean, okay, or sample proportion, which is the sum of them over N, okay, it just over N, that is over N square, they cancel out. So that's why we have this formula, okay? So maybe a little bit abstract, okay? Let us go to the example, then you will see how we use it, okay? Now, this proportion is 0.6, okay? And the sample size 100, okay? And asking what is the sample proportion is less than 0.55, okay? And first you track N pi 60, okay? And N times 1 minus pi is 40. So it's more than 5. So you can apply the approximation or the central limit theorem, which sets p less than 0.55. It just convert to z. Okay. This minus the mean, okay, which is this guy, this sample proportion, okay, because p will be normal, right? Pi times 1 minus pi over n, okay, and you take square, you take the this is variance, right? So take the square root of this. So you simplify it, give you this number, and again use the Excel, you get the answer. Is that okay? This is just telling you that sample proportion, you can easily get the answer. Okay, any question? No? Okay, sounds good. Since looks like you guys are pretty good. So the last part is not complicated, okay? Again, just, we don't really prove it, but we just provide you a result, okay? So there's nothing to understand or not, but just to remember. So if xn, a simple random sample from normal, okay? So then, right, if it's from normal, the sample mean will also be normal, right? Because we know sum of the normal is normal, right? So the sum of the normal divided by n will be the same idea here. Okay, because x1 has normal mu sigma, x2 is also mu sigma, right? So x1 plus x2 will be 2 mu 2 sigma square, okay? And if you just have the average, right, which is x bar, if you own 2 of them, will be mu sigma square over 2, okay? So in this case, this from the central limit theorem, or in this case will be N01, right? This is something even without central limit theorem, but the central limit theorem said, even if we forget about this assumption, okay, this is also true. Okay, so that is the main thing about central limit theorem. Okay, and the difficult part is as we said beginning, this sometimes we can make some conjecture on this, but sometimes it's very hard to make conjecture on this. What should be sample variance, right? The sample mean is easy to calculate because we know the sample mean is unbiased. So if we do a lot of sample and we do a lot of the average, then we have some idea sample mean. But the variance is sometimes we don't know. Okay, so and very often, right? It's very natural to replace this population variance by sample variance. Okay, and the question is, what is this distribution? What's that? Okay, what's this guy? Okay, the answer is this guy indeed turned out to be something we have learned last class. Is it follow what we call the T distribution. Okay, so this is very important discovery in 120 years ago. Okay, turned out to be what the student, okay, not you, but a statistician, shows that this is indeed following T distribution, okay? With degree of n minus 1. You have n data, then it's n minus 1, okay? So that is something we need to remember, and we don't try to prove it, but we give you some idea how we prove it. So this is the main thing about this chapter, okay? Two things. This is normal CO1, okay? It's from central limit theorem. So this is the main thing we learned today. And the second is if you replace sigma by S, it will follow a T. Is that clear? This is the single most important thing in this class. And of course, if X, the data is either 0 or 1, okay, with sample proportion, we also have somewhat other simple technique, right? It would be something like the pi, 1 minus pi over n is also normal CO1, okay? So that is the three equation that you need to remember, okay? And the next thing is I want to go to the next slide. Is that okay? Any question? Okay. Maybe I go to the next slide and talk a little bit about the example. Okay. So the population of sample mean 5. Okay. Mu is 5. Okay. And the sample size n is 100. Okay. And the sample variance is 8. So which means that S squared is 8. Okay. And what is population sample mean? It's no more than 4.5. Okay. If we know the sigma square, then we can apply central limit theorem, but we don't. So turn out we need to rely the T. Okay. So turn out that X. Okay. We will be saying this X bar minus this sample mean. This is 5. Okay. Divided by 8 over 100, okay, will follow the T 100 minus 1, which is T99, okay? Okay, now you apply this transformation to the both sides, so that's why you would do this, okay? This become T, okay? And turn out to be, this is negative 1.68, okay? And actually turn out when T is very big, it's close to Z, okay? But I want to show you how to do this in Excel with the T, and then we will end this class, okay? We'll end this here. So I just want to show you this particular example, okay? So here we will be using the T distribution, T dot this, okay? And then we have negative 1.769, and then degree of freedom 99, okay? And then again, this is true, okay? The only difference here is we need to input the sample size minus 1 as second argument, okay? That's why the comma 99, okay? So let's copy here, okay? So, and then actually you can see the norm as this, okay? Negative 1.7968 and true, okay? Also give you a very similar answer, okay? So that's why 1.796, 8, okay? So Okay, so that should be the answer there. Okay, so that's how you get the answer. Okay, so the remainder two proof, and we'll go over that in the next class. So make sure that you would you submit your homework 1. The homework 2 will be given to you shortly. I'll upload the homework 2. You will be given 2 weeks to complete. So homework 2 will be focusing on chapter 3, 4, and 5. Okay, so will 2 answer accepted? Should be the same thing, very close. The T and the, it will not be different too much. Yeah, there will be 6 assignments in total, yes. And then, as we said, we'll count the best 5 of it. So the worst one we drop. Okay, there's no, if there's no more, if there's no more question, then that's fine. So yx, some question, yx bar less than 4. What, next bar less than 4? Sorry. I mean, in case those who want to leave can leave. Thank you. Bye-bye. Have a nice weekend. Kaka, can you say what is by x bar less than 4? Yeah, thank you. Have a nice weekend. So homework 1, the homework 2 we uploaded. I'll put a message on the Blackboard.
Professor. I want to ask why for the question.
So 4.5. Sorry. Yeah, 4.5. Sorry, typo. Yeah, thanks. It's 4.5. Sorry.
Professor， 可唔可以問一個問題？
好，請問。
我想問 norm disk 咧幾時係用 true， 幾時用 false 嘅？因為我記得你話我哋通常會用 true， 但係我上網揾咧，我想整 SD graph 啦，佢係用 false。
應該冇機會用 false 喺你哋嘅情況之下。
如果係整 SD curve 咧
？SD true 係咩意思啊？好唔好？
唔係 SD curve， 即係嗰條線 bell curve。
即係你話個 Excel 係咪你話緊呢度？你係咪話緊呢度幾時用 false 啊？
係啊。
你基本上冇機會用到 false 㗎，因為佢 false 嘅意思係話嗰個 density 嘅高度啊嘛。你唔會用 density 嘅高度㗎。
因為我上網睇到我想整 SD curve 啦，跟住佢好似我見到幾個網都係用 false 嘅。
咩叫 SD curve 啊？你講緊邊一個 SD curve 啊
？Standard deviation curve。
我哋冇教過呢樣嘢係嘛？
冇啊，我上網揾。
唔需，我哋係喺我哋嘅用途係唔需要嘅，因為計 probability 嗰陣冇用嘅呢嚿嘢。
OK。因為阿 Simon 我想試下整呢個，但係咪冇用㗎？
喺我哋嘅用途冇用，好少用得到嘅，因為個 density 嚟㗎嘛，嗰個係。
OK，
即係我諗我未用過咯。老實講，我實用上冇用到嘅，冇用過嘅，除非你就個 integrate 應該冇乜特別大用。
OK， 好 ，thank you。
Professor 係。
OK， 等我覆緊個問題。OK， 得你講。
我想問係咪assignment 1你話嗰啲 source data source 咧就寫喺一個 report 嗰個 data 嘅右下角，好似頭先你咁講。
左下角嗰度就係最簡單，就個 source 喺邊度啫嘛，唔係好複雜啫嘛，就係 source。
跟住 個 detail source 就寫翻喺個 Excel 度咁。
係啦，冇錯。
哦，好啊好啊，唔該。
OK。
同埋present 嗰個 video 咧，係咪話你用咩形式 present 都得㗎？
你隨便你啦，你點都得㗎啦，就係想去讓你自己練一下點樣 present 啫。即係你想將全部 slide 就得，你想乜都點都得，隨你點做就得，冇限制。
好好，唔該。
有發揮。
我想講翻即係嗰個
乜大聲少少 ，sorry。
我想講翻嗰個 quiz 咧，上一堂嗰個我諗住睇翻個答案，但佢又重新開，即係佢重新開始咗，但我冇做到，佢就變咗0分咯。咁呢個點啊？呢個應該即係由得佢定係？
你由得佢咯，我諗佢應該有呢個記錄嘅嚇。
哦，好啊好啊。
如果你有擔心，你咪做一次咯，冇影響嘅應該。
哦，好。
如果你答係咯，應該冇影響，應該有記錄低嘅。
好，唔該。
Professor， 唔好意思，我想問多次啦。如果我想比較可能分數嘅差距啦，用 SD 係咪直接用個數字就得啦？即係整喺個份 poster 度。咩
差距？唔係好明，你再講一次。
因為我想比較下個分數差距，即係可能 DSE 分數差距，跟住我想用 SD。
點解 SD 會有用咧？比較差距。
睇下個分數差距大唔大？
即係 standard score 係嘛？即係 1 over SD 係咪咁嘅意思？係咯，就係正常就係 standard score 嘛 ，standard score 係啊，即係係啊，冇係可以咁做啊。係，但係可唔可以用個圖嚟即係比較？即係我想比較3間大學，因為比較3間大學。
係啊。
我諗我唔係太理解你嘅問題，就我咧嘗試理解你嘅問題。
Okay.
係有個 data 啦，譬如話港大係咯，你係咪跟住咧？跟住就係跟住你有個 SD 係嘛？
係。
即係你有每一間大學嘅 mean 係咪 SD 係咪？
係。
咁你係想做咩？
我想整個 curve 出嚟比較佢哋邊個 SD 大啲。定係就咁 list 個數就？如果得3個數字，咁你個 curve 唔係太大用嘅啫喎。除非你係話想 scatter plot 話佢嘅 mean 佢嘅 SD， 咁你可能有啲嘢可以講下嘅，係咪？即係譬如話，如果港大喺度，或者中大喺度，港大喺度，我亂噏啦 US 喺度，咁你可以講下嘢咯。OK。但係我唔知你個 plot。如果得一個 data，我唔知你想點樣，即係得3個點，我唔知你想點 plot 咯。OK， 係咪唔可以用 bell curve 㗎？但係得3個點，你點 bell 咧？如果你係好多個，譬如話你有8間院校咁，可以 bell 下嘅。即係如果有8間院校，你可能有啲 data 可以畫個可能畫到一個 bell 嘅。但係正常嚟講，如果得嗰幾個點嘅話，通常唔會畫 bell 嘅，因為幾點直接你哋 table 又得，或者畫個 bar chart 就 OK 㗎啦。我唔知你想做咩啦，但係你畫個 curve， 你想表達一嚿嘢㗎嘛，係咪先？即係你嘅重心想表達咩，咁你可以，咁你就按住個嚟整圖咯。我可唔可以喺度畫出嚟啊？你可以㗎，你可以直接喺 Anthony 可以嘅。呢個咁樣，例如咯，可能一間 CU 嘅 Hong Kong U。咁你就唔係 SD 咯，你呢個係你呢個 distribution 啊？即係你唔係個 data，你個 data 係話 HKU 你有一堆數據喺度 ，CHK 有一堆數據喺度，UST 有一堆數據喺度。係呢個係。你即係有成堆數據喺度嘅。係啊。咁你即係 plot 個 frequency polygon 啫，其實只係或者個啲 hit 數據係咁解啫。即係你可能係咁樣 CHK 咁樣。係，就係咁樣。跟住我上網揾佢係嗰個用 force 嘅咯。佢係 normalize 咗之後。係 norm disk 跟住用 force 咯，佢係。OK。佢係 OK， 佢係。做緊第二樣嘢，佢係即係話佢 assume 佢係 normal， 佢做好多嘢喺度嘅。佢做 assume 佢 normal 之後，佢畫翻個
相對應翻嗰個喺邊度位嘅。所以其實你就 normalize 得㗎，你係想做嗰樣嘢係嘛？你係佢係同一個。
應該係。
如果佢 normalize，所以你 normalize 過就得啦，你就 normalize 就得啦。我唔知係咪你嘅意思。
OK，我試下，再試下做。你
試一試，因為我諗佢係 normalize 咗，你就 normalize 咗之後再畫得㗎啦，即係你 minus 個 mean divided by SDL， 跟住照畫就畫喺同一個 curve 就啱㗎啦。我諗應該係咁嘅意思。
OK，thank you。
OK。Any more questions?